Hello, YouTube viewers. Welcome to my show, Rocket Monday. In today's episode, we're going to talk about reaction control system. So let's dive right into it. Well, first you have to understand space itself. Well, what is it? Simple answer, there is nothing in it. That's the whole reality of it. There is nothing. It's a void. That is why we call it vacuum. So you have nothing. So what does that mean for anything that you send in space, be it International Space Station, be it Dragon Capsule, be it BFR? What does it mean for them? Well, you cannot have what we classify as control surfaces. If you are familiar with aircraft, have you ever seen any aircraft? You must have seen what we classify as control surfaces. Basically, things like at the end, end of your airplane wings, their tail, and all that. All these things provide control. That's why we call them control surfaces. Now they work on simple principle of action equals reaction, but they react against atmosphere. Once you are in space, there is no atmosphere, so you cannot do that anything like with it. Basically, you can have a space plane that goes that high, but here's the deal: once you are in that space, you have no control. Basically, you can't do anything. It will be like flapping your hand, and nothing will happen. So we cannot employ normal surface control. Now, is it important? Well, think of it this way. Let's say International Space Station is there, and if it has no way of controlling itself, how the heck it's gonna align the solar panels perfectly to the sun? And during the nighttime, basically nighttime of ISS, when it goes into Earth's shadow, they align the solar panel in the same plane as orbit. So basically they make it perpendicular is the wrong word, parallel to the orbit plane, so it has less drag. They have to do this every every orbit, which is like multiple times a day. So you can understand that it is very critical. On top of that, let's say talk about geostationary, which is literally on top of this, and that is like 36,000 kilometer and all that. That also has to maintain its solar panels, because yes, dish can be focusing directly on Earth, so that's awesome, nothing to that, but it has to rotate the solar panel so it can always face the sun. And other things also is required, where you have to little bit of thrust you have to have in order to maintain your orbit, which is called orbit raising maneuvers. So you can understand that. And generally orientation is classified in three rotational axes. We have roll, when you are rolling like this. Then you have pitch, that's why we said a nose pitch up, pitch down, pitch up, and all that. And then you have yaw. Yaw is the hardest to remember. It's like something like that. So these are the three rotational axes, and you cannot achieve this using normal engine, simple because normal engine is designed to either push you forward or push you backwards. That's it. It has simple axes like that. It's like either this or this. You can again orient it in such a way that you have to get this axis also, but without basically this rotational control, you have no way of doing it. Basically, if your engine is backward, all you can do is go forwards. So this is why this three control is very important, because if you have these three control, you can aim your rear engine whatever way you want. Like let's say you want to flip and burn, you can do like this and flip and burn it. What basically Falcon 9 stage 1 booster does, flip and burn maneuver. So you have to understand there are some serious problem with space. Well, so what is the solution? Physics is very simple. Action equals reaction. Same mathematics that we apply on rockets, it can be applied here. It's the third law of motion. You cannot break it. So if you have, but side effect is that you need reaction mass of it. Basically, you have to carry something that you're gonna dump in vacuum of space, and it will not come down with you. Again, you will always carry extra, and you will be like, okay, this mission did not require that many correction and all that jazz. It could happen, but here's the deal: it's not coming back with you. It's like a propellant that you are spending in space. So you need that mass. So how much energy you can get out of it? Basically, let's say you have to turn a 20-ton spacecraft, let's say Dragon Capsule, it's less than that, but let's say 20 ton, versus if you have to turn, let's say 60 ton of space shuttle, versus something in future, let's say BFR, which is even heavier than that. How the heck you gonna get that? So you have two control factors. Basically, you can throw a lot, basically mass. Higher the mass, the more reaction you get. That's a simple. On top of that, you can throw it at higher speed. Basically, 1 kilogram sent at Mach 1 will give you a certain amount of push. 1 kilogram sent at Mach 2 will give you double the push. Actually, it will cube that. So you get the idea. So either you send a lot of mass, or you send at a very high speed. That will equal the higher push. Now, generally, you want higher speed, not higher mass, simply because that is the extra propellant that you are carrying. It's not a payload. It's not gonna pay you for you are sending a satellite, and also this 100-ton payload, they're not gonna pay SpaceX for that. So it directly cuts away from the main budget of the spacecraft. Like in lunar module, they have to have like multiple of these systems. So the propellant has to be designed in such a way that instead of relying on instead of sending hundreds of kilos, send few kilos, but send it at very fast speed, so you get higher control. And these are basically miniature rockets. So physics is very simple. It is a rocket, and it's oriented in such a way that it acts differently, but it is a miniature rocket. So that's the physics of it. So how does it work? Let's talk about the engineering aspect of it. Well, generally there are completely different requirements for these rocket versus when you are talking about the main engine rockets, because these are generally monopropellant. Why monopropellant? Well, monopropellant simply means it's mono. You don't have to carry two separate tanks. You have only one tank and that's it, your main propellant tank. And monopropellants are generally very reactive. So if you have, let's say, a monopropellant in tank number one and you have to send it to engine, if you send it there and if you have, let's say, a catalyst bed or a heating element, because generally monopropellants have a ignition temperature kind of. So if you are like freezing it to minus 500 degrees Celsius, it's not 500 is like below absolute zero, but you get the idea. Like in space it can go that cold, so you have to make sure that it is heated. So generally they will have either heated bed or catalyst bed. Generally catalyst bed is preferred because it's 100% temperature. It will not care about the temperature, so you can be like, dark side of basically earth and be like, why I'm saying earth, basically in the shadow of earth, and your temperature won't go as low as absolute zero. But if you have not absolute zero, it's just like close to that, and catalyst will still work. So generally people use catalyst bed rather than heating bed, again depending on your requirement, because catalysts are generally either palladium or platinum. Those are very expensive. So people sometimes use heated bed. We're just gonna heat the propellant in the engines, and once it's heated up, you don't have to do anything. It's like self-fulfilling reaction. So that is the whole reality. We want monopropellant. We don't want to carry hundreds of things. We just want to have one simple solution. They are generally pressure fed. It's not necessary, but generally they are pressure fed. So this is a reaction control system of space shuttle. Again, it used to pull double duty. That is why it's so big and beefy. Now you can understand, this is the fuel tank. Now what the heck is this spherical tank? Now that tank is pressurized gas. We simply pressure feed it, because if you are familiar with any of my videos about rocket engines are different from flamethrower. Why? Because the fuel and oxidizer that has been burned is being burned at high pressure and let it through a nozzle. That gives you the thrust, because if you're not pressurizing the fuel, all you're gonna get is a basically gas stove with a very expensive fuel. So how the heck you take that gas stove, turn it into a rocket engine? You pressurize it. Pressurizing is it in generally, main engines are done through turbochargers. Those are very expensive, complicated, ludicrously expensive. Here is just a tank. It's just like a 600 psi or 1200 psi, whatever have you, like whatever gas you are familiar with. Generally we use helium because it's non-reactive, so we use that to pressurize it. It's just pressure fed engine. Everything about the system has to be simple. Now I told you, like main engines, we built main engines with completely different thought process in mind. This, on the other hand, reaction control system has to be simple, so you can ignite it as many times as you want. It has to be small because you will put it everywhere in the system. Basically this is a reaction control engine for Gemini capsule, so you can see like it's literally small, like it's literally this size. So simple, small, and it has to be liquefied, because solid boosters, while they are very powerful for emergency abort, they do not have a control system where you can properly finesse your way into things. It's flat out, it's a blunt instrument. You need a precision instrument here. So long-term storage and restartability are the two secondary components that you must worry about. Now long-term storage is different for satellites versus spacecraft, because spacecraft is like, okay, it's gonna go into ISS, it's gonna dock there, in less than 6 months it's gonna come back. So that's one period. When you are talking about satellite, let's say a geostationary satellite, you could be talking about like 10 years, and it must have that propellant working at the end, so it can do what we call deorbiting burn. Not deorbiting for geostationary, it's like graveyard burn. Basically it's gonna increase its orbital speed and send it upwards. So you can understand, like it must be long-term storable. That means you cannot use cryogenic system. Even in vacuum space, your liquid methane, your liquid oxygen is gonna boil away. Again, very slowly, but it will. And in case of months or years, you will lose most of your propellant. So flat out, it is you cannot use cryogenics. And restartable. Now this is a very critical thing. Anybody who's following SpaceX development must have seen how many rockets they lost simply because they ran out of TTAP. They were using TTAP for ignition system. And in the modern Raptor engine, they are using electrical system. Again, there are many things in a normal engine. These things have to be much more simpler than that. So generally they have either heating element for heat activated system or catalyst pair, where they don't even have to do anything. They just have to open a valve and that's it. Nothing else. That's your valve is the main control system. No turbochargers, no ignition system, nothing. So that's how the engineering side of it works. So how do we implement it? Okay, we got the engine, it is small, it is compact, you have its independent fuel system and all that. How do we implement it? Well, we place nozzles everywhere, and you generally want nozzle as far apart as possible. Why? Basically, think of this way: if this is your mass, and you have to rotate it. Let's say you have to align it to something. Let's say ISS, and if somebody gives you thruster here, you don't have that much leverage. But somebody gives you here, you can turn it very easily. That is why generally the nozzles for thrust control are generally clustered everywhere. Basically, you will see at the edges. You will rarely see it in the center. You will always see it at the edges. That is the primary reason for that. You want the maximum torque you can get for minimum amount of thrust. And it also slows it down because you can't have free lunch. It also slows it down, which gives computer enough time to react. It's like, because rockets are not that precise instrument. It's not like, okay, 1 gram of, it's not electromagnet where like, okay, 1 ampere will do this, 2 ampere. It's like there is a bit of fudge factor. So we place nozzle everywhere, and generally we try to spread it out for maximum control. So if you have seen the live footage of this, and videos are available where Dragon 2 is docking on its own, you can see, like, if you are watching the video, you will see many times like multiple of light thrusters, and computer is trying to gently lay it down, because again I told you, if it hits it, both of them will be destroyed, ISS and Dragon capsule. And if you can ever find high resolution images of space shuttle, you will enjoy like how many thrusters it had. Again, it was a big craft, like physically big and physically heavy also. So it had like thrusters everywhere, and during the launch these will be covered, so it reduces the aerodynamic drag. So that is the implementation of it. Now again, do not confuse Draco engines with these engines, because Draco engines is made for either landing, abort, or slow down and things of that nature. It's not a reactionary control system. Draco is much more powerful for that. You want something precise. It's like how in microscope, if you have used it in school, you must see there is one knob that is like, big and clunky and moves a lot, and then you have a small knob that is like, fine tune it. Same thing. Reaction control systems are fine tuning agents. So what we can expect in the future? Well, simply put, right now our biggest concern is regarding the fuel. The fuel is flat out not very stable. Again, different types of fuel are used for satellite versus what is used for spacecrafts. But you can understand, you must have seen people are keep calling it like there is a 6-month limit, 6-month limit, 6-month limit. That is because of the fuel. Fuel are generally corrosive to the metal that is in the tank. So basically that simply means over a period of time, tank will start to erode, and it will become contaminated enough that engine thrust will be below a certain point, or it will flat out explode. So there is a limit to that. We want a stable fuel. That's our requirement number 1. Requirement number 2 is low corrosivity. For the same thing, like you want your spacecraft to be docked to ISS for years on end. You have to have something like that. And now another fear of that is that basically if you have very complicated chemistry change, it is inherently unstable. And when you are talking about space environment, especially if you are talking about something that will be in space for 10 years or something like that, you have to worry about radiation and all that. Radiation can also break them apart, and sometimes can cause blast and all that. So stability becomes another concern for that. You cannot use something too super duper complicated, because basically high energy particles from space will destroy it. Now, better throttle. Right now, I specified in the early 1980s and 1960s and something like that, we did not have computers that were in gigahertz. So flat out computers were like way too slow. So reaction control was like, I'm already too fast for this. But nowadays, our computer can make at least 500 adjustments. Like it can send data like to actuators and all that. Is like, okay, bro, do this and that. More than 500 times per second. Problem, our throttle is not that good. Basically at this point our computers are ahead, but throttles are not. So you can't be like, okay, give me 1 Newton, give me 0.5 Newton. It's like, okay, give me 10 Newton, then it's gonna wait for like, okay, let it fade out. Now again give me 2 Newtons. Okay, you gave me 3 Newton. Okay, I will fire this opposite one. You can see that is why the docking procedure was so slow. It takes time. Like our computers are very fast, thrusters are like still clunky. So we need better throttle. Now hydrazine, I keep saying about that, and it's very carcinogenic, very dangerous and all that. So is there a replacement for that? Well, the biggest replacement have been testing right now. It's NH3OHNO3. I have no idea what the heck it's called. Basically, it's a green propellant. If you have seen a green propellant infusion mission that was done with SpaceX and NASA, this spacecraft that was launched recently, that is what it's carrying. Basically, again, this is one part of it. This is the majority part, and they mix whatever they need with glycol or other aspect, so they can increase the performance or increases stability, because again, it has to be in space. It must be stable for long enough time. And you can see this can be handled by a human. If it spills on you, you're not gonna die. If it was basically hydrazine, you will be dead by cancer itself, or simply it will corrode through you. So future is basically we want to make this thing stable. So if you dock something, let's say a BFR or something like that, and you can be like, okay, chill, it's gonna be there for like 2-3 years. So this was my presentation on reaction control system. I hope you liked it, learned from it. In that case, please click a like button. If you didn't like it, didn't enjoy it, I'd urge you to press dislike, press it twice to show me your extra disappointment, and please leave a comment because I reply to all of them. Subscribe, press the bell icon if you're free, and as always, thanks for watching.